Galaxy clusters are the largest gravitationally bound structures in the universe, vast assemblies weighing between 100 trillion and a few thousand trillion times the mass of the Sun, held together within a region a few million light-years across. And they are not scattered at random. They sit at the densest knots of the cosmic web, a sponge-like network of luminous filaments and sheets threaded around enormous, nearly empty voids, into which all the matter of the universe has slowly organized itself under gravity. This chapter follows the physics of these bound systems, from modest groups like our own up to the great clusters. It dissects the hot, X-ray bright gas that is their true baryonic bulk, and it traces the discovery of dark matter through three independent and now concordant ways of weighing a cluster. It examines the bullet cluster, the single most direct evidence that dark matter is real, and then zooms out to the growth of the cosmic web itself and the tensions that trouble our standard picture of the universe. Bound systems of galaxies form a continuous sequence rather than sharp categories. At the small end are galaxy groups, a few dozen bright members within a million light-years or so. Our own local group, dominated by the Milky Way and the Andromeda galaxy, is the archetype, holding some 80 confirmed members, most of them faint dwarfs. Its total mass is estimated by an elegant timing argument that treats the Milky Way and Andromeda as a two-body system which flew apart after the Big Bang, was decelerated by their mutual gravity, and is now falling back together, the deceleration betraying a mass of a few trillion suns, most of it dark. At the top of the hierarchy sit the rich clusters, hundreds to thousands of galaxies bound within a few million light-years. The nearest large one, Virgo, holds well over 1,000 galaxies. The richer Coma cluster weighs 1 to 2,000 trillion suns. Yet to call a cluster a collection of galaxies is deeply misleading, and the mass budget shows why. Only 1 or 2% of a cluster's mass is in the stars of its galaxies. Another 10 to 15% is hot diffuse gas between the galaxies, and the remaining 85% or so is dark matter. A galaxy cluster is best understood not as a swarm of galaxies at all, but as an enormous well of dark matter gravity, filled with hot plasma, in which the visible galaxies are minor, glittering tracers. Because a cluster has no sharp edge, astronomers must define its mass and radius by convention, typically as the sphere within which the average density is some fixed multiple of the mean density of the universe, and the dark matter itself is arranged in a characteristic way, dense in the center and thinning outward in a universal profile that cosmological simulations reproduce for halos of every scale, from a single galaxy up to the greatest cluster. The first quantitative evidence for all this unseen mass came from cluster dynamics in 1933, when Fritz Zwicky turned his attention to the Coma cluster. Measuring the redshifts of its galaxies, he found them flying about at enormous speeds, a spread of around 1,000 kilometers a second. He then applied the virial theorem, the classical relation which, for any stable, self-gravitating system, ties the kinetic energy of its members to the depth of the gravitational well that holds them. The faster the galaxies move, the more mass is needed to keep them bound, and the mass the theorem demanded was staggering, 100 times or more the mass visible in all the cluster's stars. Zwicky concluded that Coma must be filled with vast quantities of what he called, in German, Dunkelmaterie, dark matter. It was one of the most prophetic inferences in the history of science, and it went largely ignored for 40 years. The power of the method and its peril both lie in a single feature. The mass depends on the square of the measured velocity. A cluster whose galaxies scatter at 1,000 kilometers a second, spread across a few million light-years, works out to a mass of well over 1,000 trillion suns, reproducing the canonical cluster scale from little more than a few redshifts and a size. But that sensitivity to velocity also makes the estimate fragile, an ongoing merger. Galaxies that only appear to belong to the cluster but lie in front or behind, or a lopsided distribution of orbits can all skew the answer. What redeems the dynamical mass is that it is only one of 3 independent windows onto the same gravitational well. The galaxy's motions, the temperature of the hot gas, and the bending of light by the cluster's gravity are not separate quantities but 3 readings of one underlying mass, and their agreement is a powerful check that the invisible mass is genuinely there. Consider the second window, the hot gas. Most of a cluster's ordinary matter is not in galaxies at all, but in a diffuse, almost fully ionized plasma that fills the space between them, the intracluster medium, heated by the sheer depth of the cluster's gravitational well as it collapsed. This gas reaches temperatures of tens of millions to 100 million degrees, so hot that it glows not in visible light, but in X-rays. A cluster is thus one of the brightest extended X-ray sources in the whole sky, and all sky X-ray surveys are among the most efficient ways to find clusters at all. The gas radiates as its electrons are deflected in the electric fields of ions, and the high energy cutoff of that radiation is a direct thermometer of its temperature, while the total brightness depends on the square of the gas density. That same hot gas gives a second, independent way to weigh the cluster. If the plasma is in balance, its outward pressure everywhere supporting it against the inward pull of gravity, then the run of its density and temperature with radius directly betrays the total mass pulling on it. This X-ray mass needs only the gas profiles, both measurable by X-ray telescopes like Chandra. Its one weakness is the assumption of perfect balance. Residual turbulence and bulk motions in the gas provide a little extra support that, if ignored, makes the mass come out some 10 to 20% too low. The gas carries a further gift, too, a record of cosmic chemistry. Its X-ray spectrum is studded with emission lines from iron and other heavy elements, forged in the supernova of the cluster's galaxies and blown out to enrich the whole volume. Because a cluster retains essentially every atom its galaxies ever made, its gas is one of the cleanest fossil records we have of the integrated history of star formation. There is yet a third way the hot gas announces itself, through one of the most beautiful effects in cosmology. As the cosmic microwave background, the relic radiation of the Big Bang, passes through a cluster, a small fraction of its photons collide with the hot, fast-moving electrons of the gas and are kicked to higher energy. This is the Sunyaev-Zeldovich effect, and it leaves a tiny, characteristic dent in the background spectrum. The cluster appears as a faint, cool shadow at low frequencies and a bright spot at high ones. Two features make it extraordinarily useful. First, because it is a distortion of a background that fills all of space. Its strength does not fade with distance, so a survey can find clusters of a given mass equally well no matter how far away they are. Second, its total signal measures the entire thermal energy of the gas, making it a clean proxy for mass. Telescopes at the South Pole and in the Atacama Desert, and the Planck satellite, have catalogued thousands of clusters this way, from a signal amounting to a change of only a few parts in 100,000. In the dense hearts of many clusters, the gas is packed so tightly that it should cool and lose pressure within the age of the universe, whereupon gas from farther out ought to come flooding inward. A cooling flow that was once predicted to dump hundreds of suns' worth of cold gas onto the central galaxy every year. But when high-resolution X-ray spectroscopy went looking for the telltale signatures of gas cooling, the way down they were almost entirely absent. This cooling flow problem demanded a hidden heat source, and the culprit is now clear: the supermassive black hole at the heart of the central galaxy. As gas cools and accretes onto it, the black hole launches jets that inflate great buoyant bubbles in the surrounding plasma, bubbles seen directly as cavities in the X-ray images, and the energy they deposit reheats the gas and shuts the cooling down. It is a self-regulating thermostat. Cooling feeds the black hole and the black hole heats the gas that would otherwise cool. The same feedback that solves the cooling flow problem also explains why the giant galaxies at cluster centers are old and red rather than furiously forming stars. The third and most powerful way to weigh a cluster relies on general relativity itself. Mass bends spacetime and therefore bends light. Clusters, the most massive concentrations of matter in the universe, are the most powerful gravitational lenses, and lensing has a unique virtue. It responds to all the mass, dark or luminous, and needs no assumption whatever that the cluster be settled or in balance. The gravity of the cluster distorts the images of galaxies lying far behind it, and the pattern of that distortion maps the intervening mass. In the dense core, the lensing is dramatic. Background galaxies are smeared into brilliant, magnified arcs, and modelling them pins down the central mass with great precision. Farther out, the effect is far too weak to see in any single galaxy, but the faint, coherent stretching imprinted on many thousands of background galaxies can be teased out statistically, mapping the cluster's mass all the way to its edge and beyond. That freedom from any assumption of equilibrium is what makes lensing the gold standard. The dynamical and X-ray methods both presuppose a settled system. Lensing weighs even a violently merging cluster honestly. It has two subtleties of its own. It measures only the mass projected along the line of sight, so a cluster stretched toward us looks heavier than it is, and it needs external information to fix the absolute scale. but averaged over many clusters these wash out, and lensing has become the anchor that calibrates all the other mass measures. As a bonus, a massive cluster acts as a natural telescope, its magnification revealing faint, distant galaxies behind it that no instrument could otherwise see, a trick the Hubble and Webb telescopes have used to peer into the early universe. And it was lensing that settled the dark matter question most dramatically of all, in a single shattered object. That object is the bullet cluster, two clusters caught in the act, a few 100 million years after a head-on collision at thousands of kilometers a second. The collision sorts the clusters, ingredients by how they interact. The galaxies, tiny targets in a vast volume, sail through one another almost untouched, and so if it is collisionless does the dark matter. But the hot gas being a fluid cannot. The two gas clouds smash together, shock, and are slowed by the drag, lagging behind while a sharp bow shock, shaped like a bullet, marks the smaller cluster's gas ploughing through the larger. The gas, which holds most of the ordinary matter, ends up stranded in the middle, between the two sets of galaxies that have raced on ahead. Now comes the decisive step. An X-ray image shows exactly where the gas, the bulk of the visible matter, has ended up. A lensing map made with no assumption about the cluster's state shows exactly where the gravitating mass is, and the two do not coincide. The gravity is not centered on the gas where most of the visible matter lies, it is centered on the galaxies which have passed clean through. The dominant mass is displaced from the dominant baryons, exactly as expected if each cluster is wrapped in a halo of collisionless dark matter that sailed through the collision with the galaxies. This is extraordinarily hard to explain by modifying gravity while keeping all the mass tied to the ordinary matter, for then the gravity should track the gas. The bullet cluster is therefore the most direct evidence we have that dark matter is real and collisionless, though what particle it is made of remains entirely unknown. Zoom out from any single cluster, and the clusters themselves fall into a grander pattern, the cosmic web. Galaxy surveys mapping the sky in 3 dimensions revealed that galaxies and clusters are not sprinkled evenly, but strung along a filigree of filaments and sheets meeting at dense nodes where the clusters sit, and surrounding vast, nearly empty voids that fill most of the volume of space. This architecture grew from almost nothing. The early universe was very nearly uniform, marked only by density ripples of about 1 part in 100,000. Gravity patiently amplified them, and because collapse always proceeds fastest along the direction of steepest squeezing, it is intrinsically lopsided. A region first collapses along its thinnest dimension into a flat sheet, then along the next into a filament, and, finally where filaments cross, into a compact cluster at a node. Matter drains out of the emptying voids, along the walls into the filaments, and finally onto the clusters, which grow to this day, by feeding along the very filaments that thread the web. This whole picture is reproduced, in breathtaking detail, by cosmological simulations that follow billions of particles collapsing under gravity from smooth initial conditions. The filaments and the clusters at their nodes emerging together exactly as observed. What survives as a precise number is the matter-power spectrum, the statistical fingerprint of how strongly matter clumps on each scale, whose overall amplitude is a key cosmological parameter. Even the voids are informative rather than empty of meaning. Because their interiors are simple and only weakly touched by messy gas physics, their shapes and sizes have become clean probes of how fast structure grows and of whether gravity behaves as Einstein said. Comparing the observed clumpiness of the universe against theory constrains the density of matter and the nature of dark energy at once. Woven into the web is a faint but exquisitely predictable feature, the baryon acoustic oscillation scale. Before the universe became transparent, it was a hot plasma in which sound waves rippled outward from every density peak driven by the pressure of light against the infalling matter. When the universe cooled and the light broke free, those waves froze in place, leaving a slight preference for galaxies to sit about 500 million light-years apart, a fixed length stamped into the distribution of matter. Because that length is set by simple, well-understood early universe physics, it serves as a standard ruler, measuring how large it appears at different distances, traces the expansion history of the cosmos, and weighs the dark energy driving it. Modern surveys have now measured this ruler across billions of light-years to a precision of about 1%. Clusters offer their own, independent cosmological lever. Because they are the rarest, most extreme peaks of the density field, their sheer number is exquisitely sensitive to how much matter the universe holds and how clumpy it is. Counting clusters as a function of mass and epoch directly measures the growth of cosmic structure. The catch has always been that a cluster's mass is never seen directly but inferred from a proxy, its temperature, its X-ray brightness, its Sunyaev-Zeldovich signal, through a calibrated relation, and the accuracy of that calibration has been the limiting difficulty. This is precisely where weak lensing, indifferent to whether a cluster is settled or not, has transformed the field, anchoring the mass scale and turning cluster counts into a competitive probe of the cosmos. Not everything, however, is accounted for. One genuine puzzle is the problem of the missing baryons. The total amount of ordinary matter in the universe is pinned down tightly by early universe, yet a careful census of the local cosmos, the stars, the cold gas, the hot cluster plasma, comes up short by roughly half. The simulations suggest the rest is hiding in a warm-hot intergalactic medium, gas at intermediate temperatures, spread thinly along the filaments of the cosmic web, too tenuous and too faint to see easily. Only recently have deep observations begun to catch its glow in the filaments between clusters, gradually closing the account, though a complete and uncontested tally of the missing baryons is still being assembled. Deeper questions trouble the very framework. Our standard model of cosmology, cold dark matter plus a cosmological constant, works astonishingly well, yet it faces real strains. The Hubble tension is a stubborn, now highly significant disagreement between the expansion rate inferred from the early universe and the faster rate measured from nearby galaxies, unexplained by any single identified error. A milder tension concerns just how clumpy the matter is, with several late universe probes preferring a slightly smoother cosmos than the early universe data predict. Whether these cracks signal new physics or merely hidden measurement systematics is genuinely unresolved. And beneath it all, dark matter and dark energy, together 19/20ths of everything, remain unidentified. The achievement to hold onto in the face of all these open questions is not that the mysteries are solved, but that the framework is sound. Three completely independent ways of weighing a cluster, the motions of its galaxies, the pressure of its hot gas, and the bending of light by its gravity, agree that these are the most massive structures in the universe and that they are overwhelmingly dark. And the simple idea that gravity slowly amplified faint primordial ripples reproduces, quantitatively, the whole magnificent architecture of the cosmic web, from the clusters at its blazing nodes to the silent voids between. The galaxy clusters that Zwicky first weighed in confusion are now among our most precise laboratories for the contents and the fate of the universe itself.